Okay, let's see. So we're going to start with electromagnetism. I may do astrophysics, but it's just one task. So I'll see. I have a little bit short on time, but yeah, let's see what we're going to do. Let's at least do this task sheet. Okay. So we have this task sheet, electromagnetism, and we are going to finish this chapter. Okay, now field from a single charge. Okay, so we place Q in the point there. It's a bit not unclear, but it's there. It's because I have this extension. So it's placed there. We want to just draw the direction and the size of the electric field in the point marked with an X in the figure, right? So if I draw that figure, and I can be a little bit quick, let's see. So we have, let's draw every A, minus A, minus A, and the X is just there, point was there, point was there, point was, whoops, that was a stupid point, point was there, and point was very close there. And I want to draw direction and the size of the electric field in the point, yeah. So imagine a test charge at all of those. This one is going to be the biggest. These are going to be the second biggest. This is the next in line. And then this one is by far the smallest, right? And that should be more like that. I, of course, forgot to say that this is Q right there. Okay. These two should be the same, and this should be smaller than those two and this guy. Yeah. So the perfect drawing, but you get the idea. Okay. Drawing the R vector that you want to use to find the electric field from the charge Q to the point marked in the figure, right? So you have to just, okay. We have to draw. So this is 1R, this is 1R, and up to there is 1R, and down there is 1R, and down there. Right. That's the relative vector. That is correct, the first one. And the relative vector is also correct. Good. Okay, next task. A charge minus Q is placed in the origin. Okay, so we have a charge minus Q. He is in the origin. We have is control the R vector. That's to find the electric field from the charge in point A, 0. Then we have A, and then we also have 0, A. So that's one positive. Yeah. Oh, that was my mistake. It's A, and we have A. We want to draw the R vector to find the electric field in that point. Right. So I have R where I am. I point to me, right? Then I point to me there. And that should be also correct. It should be to the right. It should be up, just like that. Okay. Then we have the electric field in the point AA. So we want to find the electric field here, right? To find that, that is just, of course, it's just minus Q 4 pi epsilon 0. Then we have the relative vector. We just have A and A. So that's just, of course, A and A. We can substitute out A. So A can go. We can just have 1 and 1. Just like that instead. And then below, that's R cubed. And R cubed is, of course, it's 2A squared 3 over 2. Isn't that it? Yeah. Yeah, we have A squared plus A squared and that cube. Yeah, that should be, of course, correct. Right. Which means that what we have is just minus in front Q 4 pi epsilon 0. A goes away, but we still have A squared. Then we have 1 as our coordinates. And then we have 2 to the power of 3 over 2. That should be correct. Let's go. Yes, that's correct. Okay. That's entirely correct. 5. Okay, then the field from 2 charges. A charge positive Q is placed in the point 0 and minus A, and a charge minus Q is placed in the point 0 and A. Okay, so now we have 2 charges. So we have a positive charge in the point 0 and minus A. Okay, so here is, of course, minus A, and there is plus Q, and then we have A, and then we have minus Q, right? Oh, that seems stupid. Okay, and then the question is, that's stupid. Draw in the R vector that you want to use to find the electric field in the point A, 0. That's the point. So A, 0. You want to find the electric field, right, in the point A, 0, right? The electric field is going to point, it's relative, and going to point to where we are, right? It's the same as saying A and then minus, which is, of course, this guy. And then it should be this guy right there. Okay? Yes. Okay. Okay, and now draw in the sizes and direction of the electric field in the 9 points let with, just all those A's. Okay, the direction and sizes on all 9 points. So let's make 9 points. This will be 1, this is 1, this is 1 point, this is 1 point. Maybe I can just do X. X, there, it was there, it was there, it's here, and it's here. That's 9, right? Okay, and then we want the electric field. So if I am here, I imagine, what was it all the, draw in the size and direction of the electric field. Okay, so the electric field, not the R vector. So the electric field. So if I'm here, I'm a small test charge. I want to go there, but at the same time, I get pushed there, right? That means that those cancel out, and this will just go up, right? So this vector here will just go up, just like that. That means the same thing on this side. It should be this as the same size. Okay. Then in the point here, it's actually not defined, right? Just think about our R vector. That one isn't defined there for that guy. And the same is for this guy as well, right? It isn't defined there. And then, I think so. Let's go back to that later. But let's imagine the others. Those are pretty big. This should be the biggest one, of course. This just entirely gets pushed, and then it's closest to our component. So that one is pretty big. Then this guy on the left side, he wants to go there, but he gets cancelled in the direction there, which means that he just goes up. But he himself is close to this guy, which means that this doesn't entirely cancel out. It will get something like this. Yeah, it should be like this. Like that, I think. That will make sense. That means the same here. That also means the same. Let's see. What am I doing? No, I was too quick there. Let's see. He wants to just go straight there, a small charge. At the same time, he gets pushed. Okay, yeah, that my mind, it was correct. And then this guy should do the same. Right? And this guy should also, he wants to go there, right? He should do the same. That's the field, right? Yeah, that should be, let's just think about these two guys. I think they should be 0, right? It can't be defined there. That should be correct. Okay. Yeah, not defined, not defined. Those were a little bit, but otherwise it's correct. Just my yeah, I was too much in favor of this guy. Yeah, I should have just a little lower, but yeah, you get the idea. It's all right. Okay, good. 6. Now, 3 unknown charges. 3 charges here. This guy, these 3, is at -a, 0, 0 respectively. All the charges Q1, Q2, Q3 shows the electric field alongside the x-axis. Which sign do they have? So if the blue here, if you're moving along the x-axis, and the blue here is the electric field, what you can view it as is the velocity. So does the velocity here go up or down? It goes down, right? But it gets the velocity somewhere. If this was negatively charged, it should go up, right? Even if this guy was positive, because it would be more negative, so we would have a higher increase. But it's not, which means that it's the opposite. This one is positive and this one's negative. It means that he gets pulled, but it's slowing down, right? So it just slows and slows down, right? He gets some velocity from this guy, but at the same time, he gets resistance in the other way. So he actually just slows down. That's how we can think about it. Then, if you come very close from this guy, you will have a huge velocity here at the beginning because you get pulled there. If you are in the middle, remember, if you are in the middle of these, where the push and pull here, that's of course here. There's no increase or decrease there. And then when you get closer and closer to this guy, right, it's just push and more pull, and of course you're increasing again. So this is positive, this is negative. And if you, in order to get the opposite effect here, this guy have to be positive, right? Because if you start here, you have a huge velocity, and then that velocity, that tangent, will just decrease and decrease the further you get away from this guy. So positive, negative, positive then. And that is true. Okay. 7. Yeah, no, that's just introduction. Okay. Task. Charge from charge density. Spatial charge density rho is given as this piecewise function, where if our radius is less than a, so we're inside some volume, you can think of it like that, we have the density c, otherwise it's just 0, right? Okay, so make just a, yeah, what you can, yeah, that's just a sphere, right? So just a sphere. So what you can do, just draw a simple sphere in 3 dimensions, just like that. And then you go there. It's not a perfect sphere, but it works. So the sphere is charged. That is the idea. Outside the sphere, it's not charged. Okay? Yeah. And you could see here, you see it's the same idea. Yeah. Outside is rho, but here inside it's c. How much charge is inside a radius r from the origin? Okay. So if it's q, it's of course uniformly throughout. So you can think of it as q is equal to this piecewise function, right? Right, if how much charge there is for a position, so we're measuring how much charge there is at that place. That means that that piecewise function there was pretty bad. So if, or it's 4 pi, and then it's of course r cubed divided by 3 times c when r is less than a, right? That should be all right. And it's of course just 4 pi a cubed divided by 3 times c when r is bigger than or equal to a. Then we don't increase. So if inside the sphere, it can get, it's different based on how far we are, but if outside, it's just, that is just at the end. So we just use the radius, total radius there. Right, and that should be all right. Did I write c? I wrote a cubed. Yes. Yeah, that should be all right. Okay. 9. Balloon. A spherical balloon with radius a has a charge plus q. How can a model for this balloon look like? How do you describe the charge with a charge density? Okay. And charge. So it's a spherical balloon. The charge density, I would just, of course, do. I would just, of course, for Q, just integrate over the volume. It's some charge there, and then, of course, the rho times the volume, right? And it has a radius A. There's a charge positive Q, and then, of course, that density there, rho V, which is what they're asking, is just, of course, Q divided by the volume. Was it? No, the balloon. I did this mistake the last time. The balloon is, of course, surface. Why do I think that the inside is charged? The balloon. I don't know. I always think that. I'm just, when I think spherical, I always think like a ball. I never think like vacuum inside a balloon. Okay. Q, and then of course over the surface, which is just Q over, what is it? What is the surface again? It's like something 2 pi r squared, is it? That one, I never remember that one. What is that one? I actually, yeah, I searched that last time. It's 4 pi r squared, is it? That guy I don't remember. Luckily, I don't need to. 4 pi. No, now I think I will remember it. So it's 4 pi, and then of course we had A, so it's just A squared, right? What is the electrical field in the middle of the balloon? 0. Why? It's not defined there. We can't set up no electric field at the origin there, right? Also, oh, even better. We usually have that not defined, but in this case, oh, we're not actually using that not defined. In this case, if you're inside the balloon, it will just come from every direction because it's uniform, right? So all the vectors always cancel out. This is like a, what's it called, Faraday cage? Yeah, it's the same idea actually. Yeah, so that's 0. Yeah, 10. Okay, last task here. Okay, so now it's the task here. It's a long wire. So long thin wire, right? You have a long thin wire. It cuts. It is parallel to the x-axis, and it cuts the y-axis, a distance a from the x-axis. A length L, we don't know how it is, but we just state it. It's infinitely long, but it's a length L. Has a charge Q. You can assume that the wire is infinitely long. Yeah, it has a length L, but it's infinitely long. Yeah. Okay, but the charge is uniform. Yeah, we're going to use that infinite, but here it is. This weird ass wire. It's thin, but my wire, yeah, my wire is stupid, but it's all right. So up to here, that's just A, right? Yeah. And it has a charge Q. Okay, draw the system. Yeah, that's the system. Very nice. Yeah, my system is awesome. Let's find an electric field in a point R x0, 0 alongside the x-axis, right? We are going to find the electric field in some point, right? X, just the electric field in some point. That's just it. So just some random point, right? Okay. In order to find the electric field, but that feels weird. Oh, we are just, this is not task. We'll get to there. Okay. Without calculating anything, which way do you think the electric field would point? Just straight up, right? A little bit same like last time. Yeah, if I'm here and this guy's infinitely long, that means that I will get, let's see, Q, right? Q, he will push me this way, but he will also, from here, he will push me this way. So he'll just push me in one direction, right? so minus y. So the electric field, it will just point straight downward, minus y. Yeah, yes. Your friend Pia says that she wants to find the electric field position. And you can just use the position 0, 0 because the result is the same. She's correct. She's correct, right? Like I said, if it's infinitely long, it will come from all directions, and those that aren't parallel to the y-axis, those will cancel out because they go on each side, right? Okay. Let's see. Yeah, she's correct. Draw a line segment DL from some position. What is the charge for this line segment? Okay, so we have some line segment. We have some line segment here. Just some small line segment, DL. And what is the charge? What line segment and what is the charge for this line segment, right? So D, that would just be dq, right? So dq, it's equal to the same thing, right? So that will just be q over 4 pi epsilon 0, right? And that's dl. We can just use dx, of course, then. And then, of course, our relative vector, we should use the correct notation. And it was from our x position, so it was just x 0, 0. Minus, what we should use is, of course, x like that to mark that this is the guy we usually integrate over. Then we have a, and we have, of course, 0. Just like that. What am I thinking? Yeah, I was thinking about, so yeah, and then, of course, dx. We just use the notation again. Then we have all of this squared, which is just I mean cubed, which is just, of course, what we want is x squared. We have plus x, this guy squared, plus a squared, then over 3 over 2. Is that correct? That seems a bit silly, but yeah, that's the way it is. Then we have q, 4 pi. I think I may have got us ahead of myself, but yeah, it's all right. So let's see, we have, oh, no. Yeah, or, no, I made a mistake. That is not a coordinate. Yeah, I was too quick. Of course, it's x minus x as a coordinate, like that. Then we have a, there's no reason to have said, so I don't know why I wrote that. That was not cool. X minus x a, and then of course what we should have is x minus x, like that, squared, and then we should have plus a squared, and this should be 3 over 2. Yeah, I think that's it. And then of course, oh, dx. Yeah, but that should be, of course, still dx, right? That should be correct. We could have written dl, but dx is more correct in my opinion. Yeah. What is the charge? I knew I was I knew I was too far. It was the from DE was I was thinking about. Yeah. That is task. Yeah, I just did this. Yeah. I'm sorry. That was a bit silly. And why did I write x? Oh, we could just use 0. Yeah, of course, but it means the same thing, right? Okay, let's do this again. I was a bit too quick and I was thinking about too many things. And you can do a lot of nonsense. I even wrote dq. That even makes it worse. Okay, the line dl, of course. What is the charge of this line element? Of course, q is the same as rho L, and then of course dl, right? You could say dl. Yeah. What is the charge of this line segment? It's just D, so D, that's just dq. What am I thinking about? What is the charge of this line segment? So what I want is dq, which is just rho L dl, right? And rho L, let's see. Yeah, don't be a moron. Why are you a moron suddenly? What is the charge of this line segment? Why are my brain suddenly just going, yeah, just going away? I just want dq, right? The total charge is q, right? And some small dl of this line segment, right? So if I have q, right, and it's uniformly charged. Let's see, a small line element dl. What is the charge of this line segment? Isn't it just q divided by dl? Isn't that it? Let's see. Q is equal to rho L dl, right? But I just want one piece. Then dq. Let's see. Yeah, it's just q over dl. Am I a complete moron? Yeah, dq is just q divided by dl, right? ql, yeah, oh, I need, of course, the count. dq, q over l dl, that was it. Oh, yeah. That wasn't good at all. Yeah, okay, I can explain. Yeah, so we have this integral here, but what we want is dq. We don't need the integral, right? So we have then just for one piece, that's just rho L dl. Now rho L is, of course, like we did earlier, it's the density. So the density would be the whole charge divided by the surface, the whole charge divided by the volume, or the whole charge divided by the line, which means that dq is equal to q over L dl. God damn it. Okay. What is the r vector that you need to use to find the contribution from the line element dl to the electric field in the point 0, 0? Yeah, it's the same as I did there, so but we can just use it. So r, right, from 0, 0, which means that our position is just 0, 0. So we have 0, 0, and it's the relative vector, so it's minus, it's x prime to indicate a and 0. So that's the way it should be, and that's of course just minus in front of both x prime, then a, and I, of course, why did I write? I'm so used to writing in 3 dimensions, it's crazy. There we go. Yeah. Yes. That is the way it should be, minus, and then x comma a, just like that. Okay, so that's the r. I did that correct? Yeah, we have r, contribution 0, 0, that should be correct. Yeah, thank God. What is the contribution dE from the field, from the E field of this slide and segment? Yeah, then we can just combine what we had. So dE, again, not the integral. So all we need is that charge, the same thing we had. We can just use Q over L. dl, we can just say what this is just Q over 4 pi epsilon 0, and then of course the position, and we have minus in front, so I can just use minus there. We have x prime, we have a, just like that, and then we are dividing, of course, just by the same thing I had last time. x prime squared plus a squared, and then 3 over 2. And then, of course, this should be in the x direction, so dx like that. That should be correct. Yes, sir. I didn't write. Oh, there's dx. I was like, where are dx here? Right. And they didn't put minus in front. I just put minus in front, but that's all right. Then we're going to write the integral from the e field. And you can write the coordinate form. Yeah, you don't need that. Okay. The integral is just the same thing from minus infinity to infinity. You know what? I just keep minus there because it's a bit prettier. So we could just say minus there minus a. Then we have x dot squared plus a squared. Then we have 3 over 2 dx like that. That should be correct. Got that answer. Yes, it is. They use q over l. Why did they just use... Why did you use q over l? You didn't... Oh, my days. I should have just used q over l. It was the density should have been there. Oh, yeah. I missed. I was too quick again. Yeah. That was not good. Why are you so fast suddenly, right? I was thinking in completely different terms. Of course it's Q over L. It's the density, right? My mistake. Yeah, of course. The integral is, of course, it's rho for what we have, right? And then we have 4 pi epsilon 0. Then I would have, of course, r, and then r cubed, and then, of course, in our case, it would be dl. So I should have substituted for rho. I just inserted q because I wasn't thinking. Yeah, that wasn't good. It has to be better tomorrow. Okay. Yeah, that's it for today, and I'll see you tomorrow.